I decided I wanted a nice big boring bar to suit the Multifix 30mm boring bar holder. Rather than machine an insert holder from scratch, I went on eBay and found a Capto C3 cartridge. Capto is really quite nice. It has a rigid taper and face contact like a HSK, but also has a polygonal tapered shaft to transmit torque. This makes it the interface of choice for mill turn machines, but it is also popular for CNC lathes and in milling spindles. This one isn't the ideal geometry for a boring bar. I got it because I have a suitable inserts and it was the cheapest listed at the time. An advantage of Capto over HSK, from my point of view, is that it can be held in place by a simple threaded drawbar, though they also have the option to be retained by an expanding drawbar along the same lines as HSK. I will go into more details of how the shape is generated later in the video, probably too much detail, but here is my tweaked 9065 Holbrook miner creating the receiver cavity in the end of 30mm AN8 bar. Measuring how much gap there was to pull up was a nice job for my JSA Slotmaster slot measuring gauge, bought in a moment of eBay weakness. I had a lot of trouble finding the definition for the shape of the polygon. At first I tried modelling it as a roller triangle, but that wasn't quite right. Capto shank is a standard, defined in ISO 26623, but I didn't want to pay £130 for that, for what is basically messing around at home. Eventually I found a PDF on a Polish government website, and that had an equation. Unfortunately, when I plotted the equation in Excel, it wasn't anything like the right shape. But this turned out just to be a case of a minus sign that should have been a plus. At this point I thought I was home and dry. It would just be a case of feeding the lathe spindle angle into a Linux CNC HAL component, do a bit of trigonometry, and job done. When I tried to model this, it didn't work. The points that make up the curve are calculated at even intervals in the generator angle, but the actual points are not evenly spaced around the centre point of the figure. This makes sense if you look at the equation. It is the equation for a circle of the nominal diameter of the shank, 22mm in the case of C3, but then a smaller circle of radius 2e, where e is the eccentricity, 0.7mm for C3, rotating at twice the speed. And then a second circle of radius e running at 4 times the speed. In the animation you can see the blue-grey dot revolving around a circle, whilst the red dot traces out the shape of the Capto shank. The red dot alternately leads and lags the blue-grey dot, and this means that generating the shape isn't as easy as I had anticipated. To be useful to me, I needed the data at evenly spaced intervals, so after trying and failing to find an analytical solution, I went back to Excel and used some Visual Basic to solve for x and y at fixed angular increments using successive approximation. If you were to look carefully, you would see that there are 100 evenly spaced orange dots on the same curve as the grey dots. I used the Excel code to create lookup tables for x and y offsets to use with a mill machine and boring head, and radial offsets to use with a lathe. These were formatted into C code and pasted into a Linux CNC HAL component. Here we see the X offsets for the various different sizes of Capto interfaces, and then the Y offsets, and the radial ones. The lookup tables make the offset calculation very quick and efficient. A simple linear interpolation is used between data points. I have posted the component on GitHub, link in the description.